We know that when a signal is applied to the inverting input of an op-amp, the output is 180 degrees out of phase with the input, whereas when a signal is applied to the non-inverting input, the output is in phase with the input. If signals are applied simultaneously to both the non-inverting and inverting inputs, the output will reflect a combination of positive and negative contributions, thereby performing a differencing operation. As shown in the diagram, this circuit is designed to subtract two voltages, V1 and V2, and is therefore called a differential amplifier. Structurally, it combines the inverting and non-inverting input configurations into a single amplifier. Applying the concepts of virtual short, virtual open, and Kirchhoff's current law at points N and P, we obtain I1 equals I4, I2 equals I3, Vn equals Vp. The difference between Vi1 and Vn divided by R1 equals the difference between Vn and Vo divided by R4. The difference between Vi2 and Vp divided by R2 equals the difference between Vp and 0 divided by R3. So, we have Vo equals the sum of R1 and R4 divided by R1, times R3 divided by the sum of R2 and R3, times Vi2, minus R4 divided by R1 times Vi1. When the ratio of R4 to R1 equals the ratio of R3 to R2, Vo equals R4 divided by R1 times Vi2 minus Vi1. The output voltage is directly proportional to the difference between the two input voltages, which is why this circuit is called a differential proportional amplifier. If R4 equals R1, then Vo equals Vi2 minus Vi1, and the circuit performs a subtraction operation. From the amplifier's perspective, the gain is AVD, which is the ratio of Vo to the difference between Vi2 and Vi1, equaling R4 divided by R1. This circuit is therefore also referred to as a differential amplifier or a subtractor circuit. When the ratio of R4 to R1 equals the ratio of R3 to R2, the differential input voltage VID equals Vi2 minus Vi1. At this time, IID equals I2 equals I3 equals negative I1 equals negative I4. VID equals IID times the sum of R2 and R3 minus VO minus IID times the sum of R1 and R4. VP equals IID times R2. Vn equals Vo minus IID times R4. Vp equals Vn, the differential input resistance. RID equals VID divided by IID, which equals the sum of R1 and R2. Since the larger the resistance values of R1 and R2, the smaller the gain, they cannot be increased without limit. As a result, the input resistance of this circuit is usually not very high. How can we increase the input resistance? To improve the input resistance, a voltage follower is often connected at the front end. The input resistance becomes that of the voltage follower, taking advantage of its high input resistance to raise the overall input resistance. Because the op-amp's output resistance RO equals 0, the circuit's output resistance RO is also 0. The instrumentation amplifier is shown in the diagram, where A1 and A2 form the first stage amplifier, with V1 and V2 as its inputs and V3 and V4 as its outputs. The second stage, formed by A3, is a differencing amplifier. For the first stage, using the virtual short and virtual open characteristics of an ideal op-amp, we have IP equals IN equals 0, VO1 equals V1, VO2 equals V2, and the current through R1 and the two R2 resistors is equal, that is, IR1 equals IR2 equals the difference between VO1 and VO2 divided by R1 equals the difference between V1 and V2 divided by R1. Therefore, we have V3 minus V4 equals IR1 times R1 plus 2 times IR2 times R2, which equals 1 plus 2 times R2 over R1, all multiplied by the difference between V1 and V2. It can be seen that the difference in the output voltage of the first stage is an amplification of the difference in the input voltage. For the second stage's difference calculation, replacing V3 minus V4 with Vi1 minus Vi2 and R3 with R1 in the differencing amplifier, we get VO equals negative R4 over R3 times the difference between V3 and V4, which is equal to negative R4 over R3 times 1 plus 2 times R2 over R1, all multiplied by the difference between V1 and V2. Thus, the voltage gain of the circuit is AV equals the ratio of VO to the difference between V1 and V2, which is equal to negative R4 over R3 times 1 plus 2 times R2 over R1. Similar to the differencing amplifier, this gain is also the differential mode voltage gain, which indicates that the instrumentation amplifier has a strong ability to reject common mode signals. It is widely used in measurement systems. If multiple signals are applied to both the non-inverting and inverting inputs of the op-amp, an addition-subtraction operation circuit can be obtained. Based on what we have learned about addition and subtraction circuits, you can apply the concepts of an ideal op-amp's virtual short and virtual open to work out the results on your own after class. That concludes today's lesson. See you next time.